Hello everyone, this is Yeshi. I'm glad to attend this 2022 NUS virtual PhD show. I'm a recent graduate from NUS BME under the supervision of Prof. James Goh, and I will introduce you my PhD project, Functional Silk-Based Fibrous Scaffolds for Cardiac Tissue Regeneration. So first is a background introduction of my PhD project. Cardiovascular disease are still the leading cause of death and huge burdens globally. Atherosclerosis is the most common reason for ischemic heart disease. Stiff scar tissue will develop to replace the loss of cardiomyocytes due to ischemia, which greatly restricts the heart contraction and eventually lead to a higher chance of heart failure. Current treatments include using drugs, implanted devices, and organ transplants, but they have their limitations and it's not a sustainable strategy. So cardiac tissue engineering aims to use different strategies based on biomaterials and cells as alternative treatments. Among them, scaffold-based cardiac patch can achieve a higher cell retention rate. In addition, the functionality of the engineered tissue can be optimized by scaffold design, which brings more opportunities. Nevertheless, there are still many barriers along the way. One of them is arrhythmias, including the asynchrony of the cardiomyocyte contraction in vitro and also the rhythm mismatch with the native myocardium after implantation. To solve this problem, some studies used topographical cues and to induce cell alignment in order to recapitulate cardiac anystrophy. So these videos show the contraction of cardiomyocytes from neonatal rats. We isolated the cells and cultured them in vitro in tissue culture plate after purification. The cells gradually started to contract, and some typical issues include asynchrony and irregular. And this project aims to address the problem of contraction asynchrony of the in vitro regenerated myocardium based on the main strategy of scaffold-based cardiac patch. We studied the design of the scaffold in three different aspects: geometry, stiffness, and conductivity. So there are three main objectives in my studies, and this contractible cardiac patch consists of biomaterials, and cardiomyocytes will be applied to the infarcted side of the heart to replace the scar tissue. And then I will have a quick summary of the first two phases and then give a more comprehensive introduction of the last phases. So since myocardium extracellular matrix is composed of highly aligned nanofibrils, it is necessary to use nanoscale techniques to simulate the geometry. So the first phase of this project aims to fabricate nanofibrous scaffolds with controlled fiber alignment to guide the orientation of cardiomyocyte. I used electrospinning techniques to fabricate scaffolds with aligned silk fibrin fibers of nanoscale. And from the in vitro studies, cells could be guided by the fiber direction, and aligned fibers facilitated more organized zip disk in actin structure as shown in the right bottom photos here, and which resulted in stronger contractions. So other than geographical cues, another critical feature that governs the contraction is mechanical properties of the surroundings. Stiffness of the substrate is sensed by the cells through the mechanotransduction pathway, which affects cell morphology and cytoskeleton organization. Since cardiomyocytes are contractible, their deformations would exert force to the substrate. Subsequently, the elastic substrate would exert opposite reaction force to the cells. So in this phase, we intended to combine the topographical cues and mechanical cues for cardiomyocytes. We developed a easy-to-make mat-on-gel platform. So the PDMS gel was fabricated by mixing different ratio of base and catalyst to reach different stiffness according to a standard protocol. And the gel was being coated on a cover slip and cured in the oven for 2 hours, and then the silk fibrin scaffold was electrospun onto the gel surface. And then we did some in vitro study. The results show that the PDMS reduced the overall stiffness of the scaffold, and the cardiomyocytes grew on the composite with lower stiffness, had faster and more synchronized calcium transient frequency. And this model would be a good drug screening and disease model. However, most of the traditional scaffolds were made of electrically insulated materials, but myocardium possess a conductivity of about 0.3 Siemens per meter, which facilitates the propagation of action potentials and ultimately the contraction of the heart. So the insulated biomaterials would hinder the electrical signal propagation efficiency and lead to pro-arrhythmic effects. And recently, conductive materials have been investigated to be used as hybrid scaffolds to electronically bridge the gap between cell clusters. Conductive scaffolds started from the use of traditional materials like copper nanotubes and gold nanorods. And the hybrid scaffold were proved to improve intracellular calcium concentration and more gap junction expression when the scaffold was more conductive. And another option is conductive polymer, which possess a conductivity between metal and semiconductor. So in the last phase of my study, silk fibrin was used as the base material. And previously, we have fabricated polypyrrole-coated silk fibrin fibers by in situ chemical polymerization. However, the high mechanical properties restricted the contraction of the cell-seated mat. So this problem brings us to find an alternative way, and the answer is blending. There are studies blending polypyrrole into chitosan to form conductive hydrogel. However, it is seldomly used for electrospinning, mainly due to some undesired potential problems, and it is critical to find a suitable base material. So the objective of this study is to fabricate polypyrrole encapsulated silk fibrin fibers through electrospinning. And the first goal is to reduce the mechanical properties. The second goal is to investigate its function on cardiomyocytes function. Basically, the polypyrrole was blended into silk fibrin HFIP solution in different ratio for electrospinning. And then we studied the effects of these fibers and the co-effects of fibers with electrical stimulation on the cardiomyocyte. So first of all, we can see that the mats were all black, in which indicated that polypyrrole was successfully encapsulated into the silk fibrin fibers by electrospinning. And in general, the incorporation of polypyrrole reduced the fiber diameter due to the increased electrostatic forces. And comparing fibers with the same amount of polypyrrole, higher silk fibrin resulted in larger fiber diameter. And from the TEM result, we can also see that polypyrrole distributed more evenly in fibers with 7% silk fibrin than 5%. And for the mechanical properties, the incorporation of polypyrrole, it reduced the Young's modulus to about 1.5 megapascal, which is smaller than pure silk fibrin mat. However, lower silk fibrin amount resulted in higher Young's modulus. And the conductivity of the mat was measured by a 4-point probe machine, which ranged from 0.05 to 3.6 millisiemens per centimeter. It was higher than the reported polypyrrole embedded PCL electrospun fibers. And we also did a single muscle model in this study, showing that 7% polypyrrole 15 mat exhibited sufficient conductivity for electrical signal delivery. And for in vitro studies, we found that the cells managed to attach on these polypyrrole encapsulated fibers, and they spread in a similar manner to those pure silk fibrin mat. And very interesting, we find that the cells develop pseudopodia to grasp on the neighboring fibers, which resulted in a larger cell volume. And the MTT result also reflect that these fibers encourage cell metabolic activities. And excitingly, this slide shows the contraction of the cell-seated mat, especially on the mat with lower polypyrrole to silk fibrin ratio. It presented a regular contraction, and instead, only vibration was found from the mat with higher polypyrrole amount. And from immunostaining, surprisingly, we found that the polypyrrole encapsulated silk fibrin fibers seem to orientate cardiomyocytes into aligned manner. This was not expected, as the fibers were not aligned, and consequently the striations, as indicated here using the white arrows, were more homogeneous in fibers with polypyrrole. And quantificationally, compared to cells on the cell culture plate or silk fibrin mat, higher cell aspect ratio and a actin expression was observed from this polypyrrole encapsulated fibers. And next, we combined external electrical stimulation. We made a self-built setup to exert the electrical signal to the cell. And here we can see that the mats seated with human iPSC contracted stronger after being electrically stimulated, though the contraction rate slowed down. From the immunostaining, both the conductive mat and the electrical signal induced cell alignment. Since the cells on pure silk fibrin mat disassociated after electrical stimulation, we assume that the polypyrrole silk fibrin mat prevent potential damage from the external electrical signals. So in summary, polypyrrole encapsulated silk fibrin fibers were successfully fabricated with reduced Young's modulus, which was more suitable for cardiac tissue. And in terms of functional development, interesting findings include that the conductive mats required less cells to achieve contraction, and fibers induced cell orientation and prevent potential impair from electrical stimulation. And in phase 3, we also did a study to increase the biodegradability of these polypyrrole silk fibrin fibers. So for a summary for the whole project, firstly, we used silk fibrin electrospun mat with controlled fiber alignment to mimic the geometry of the native myocardium extracellular matrix. And we found that nanofibers changed cell morphology and fiber alignment guided cell orientation. And secondly, we combined geometry cue with stiffness to provide suitable mechanical surroundings for mechanotransduction. And we found that the mat on gel composite of 20 to 30 kilopascal increased calcium transient frequency, and the gel with aligned fiber induced earlier consistent transient. And next, we studied the combination of geometry and conductivity, where different polypyrrole silk fibrin composites were developed. Overall, we found by using conductive mat, lower cell seating density was needed to reach mat contraction, and the conductive mat enhanced cardiac troponin expression, induced cell alignment, and prevent cell dissociation from electrical stimulation. And based on the mechanism of grafting, we provided preliminary data to develop polypyrrole silk fibrin biodegradable conductive material. And lastly, the three features that were combined together by depositing conductive polypyrrole silk fibrin fibers on top of the gel, which showed enhanced expression of cardiac CX43, and further studies will be conducted for more functional evaluation. That's all. Thank you.